Let us solve a question on the applications of difference equations in economics. The question is, consider the supply and demand equations as Qs is equal to 4P subscript T minus 1 minus 10. This is the quantity supplied, and quantity demanded is equal to minus 5 P subscript T plus 35. Assuming that market is in equilibrium, find expressions for PT and QT when initial condition P naught is equal to 6. Is the system stable or unstable? Okay, so we have actually quantity supplied and quantity demand equations given, and we want to find out the stability of the equilibrium, whether our equilibrium is stable or not. Okay, so first thing is first, we know that at equilibrium demand should be equal to supply. Quantity demanded is minus 5 pt plus 35. It should be equal to quantity supplied, that is 4 pt minus 1. That means we have a time lag of 1 period here, minus 10. We solve it for pt first. Okay, that gives us, so minus 5t minus 5 pt is equal to, we have 4 pt minus 1 minus 10 and minus 35 comes out to be minus 45. That gives us pt will be equal to, so 4 upon 5, it will come out to be minus 0.8. If I divide minus 5 on both sides, I will get minus 0.8 p subscript t minus 1 minus minus into minus will be plus, because we are dividing with minus 5, so 45 divided by 5 is 9. So this is our what we call first order linear difference equation. It is of first order because we have the greatest time lag period of 1. Okay, and it is also linear because uh, variables are raised to the power 1 and there is no cross product of the time lags here. Okay, now given this first order linear difference equation, what is the general solution? Solution is being given by, and let me write it here, that is pt will be equal to uh, let us write p naught minus a upon 1 minus b bracket bt plus a upon 1 minus b. Okay, now what is a and b? A is this 9 and our b is this 0.8. This is our b. Okay, using this, what will be our stability condition here? So p naught is also being given us as p naught initial condition is, let me write here, p naught is equal to 6. Okay, if we solve this, and let me write it here first, so our pt will be equal to, if I write it in this fashion, so p naught is equal to 9 minus a is 9 upon 1 minus, and b is minus 0.8, it will become plus 0.8 bt, that means minus 0.8 raised power, or let's write it here. Okay, I have space here, so I should write it here. So our pt will be equal to pt, that means time path for price will be equal to p naught is being given us as 9, then we have minus a, sorry, p naught is being given us as 6, and let me write it here 6. uh, a is 9, so let's write it here 9 divided by 1 minus b, 1 minus, since b is minus 0.8, so minus into minus is plus, we will get 0.8 bracket, then in place of b t, so b is our minus 0.8 raised power t plus a again is 9 9 divided by 1 minus into minus is plus 0.8. Okay, so what is this term? It is 6 minus 9 divided by 2.8. Okay, 9 divided by 2.8, uh, rather it is 1.8 here. 9 divided by 1.8, it will come out to be, and let us see what exactly it comes out to be. So we have 9 shahmat divided by 1 divided by 18 divided by 10. So this is 9 divided by 1 into 10 upon 18. So 9 ones are 9 twos are 2 ones are 2 fives are. So this term comes out to be 5. Okay, so here it is 6 minus 5. So let's write it here. So this reduces to 6 minus 5. We have minus 0.8 t plus, it comes out to be 5. We have seen it. So our pt will be equal to 6 minus 5 is 1 minus 0.8 raised power t plus 5. Okay, so this equation is actually the definite solution of this first order linear difference equation. Okay, so the first term on the RHS is called the complementary function, and this constant here it is called the particular solution. Okay, the particular solution expresses the intertemporal level of price, and this complementary function represents the deviation from that equilibrium. Okay, for dynamic stability here, this complementary function should approach towards 0. That means for stability, this should approach to, this term should vanish here. It should approach to 0, and our particular solution will be equal to 5 here. Okay, so here we can see as t increases. Okay, if t increases in this first term, that means minus 0.8 raise power t, it will converge towards 0. Okay, so as t increases, this complementary function approaches towards 0. So we can say that the system is here stable or not. This is actually stable equilibrium. Okay, so I will also explain with graph also. Okay, and let me repeat it here. As t increases, this whole term converges or approaches towards 0. So this pt will eventually settle down to this particular solution, that is 5. Okay, so our pt will approach towards 5, and corresponding to this, what will be qt? Put pt is equal to 5 in demand function. So our qt will be equal to minus 5. In place of pt we have 5. Let's write it here, 5 plus 35. So this comes out to be 10. So our pt is equal to 5 and qt is equal to 10. Now we have seen that the system is stable or unstable. I want to make another point here. How do we see whether it is stable or not? All depends upon this b. Okay, so actually if I write it in general form, it is actually in this fashion, that is yt is equal to a b raised power t plus c. A is the arbitrary constant, or it is our constant here. So the stability of the equilibrium depends upon this base b. Here base is minus 0.8. Okay, and what are the stability conditions here? If mod of b is less than 1, time path converges, and if mod of b is greater than 1, time path explodes. I will show the graph here also. And if b is less than 0, okay, time path oscillates, okay. If b is greater than 0, time path does not oscillate, okay. Here we have seen our b is minus 0.8, so we have minus 0.8, its modulus is actually less than 1, so this condition is being satisfied. That means time path will converge. Also our b is less than 0, okay, because we have minus 0.8 is actually less than 0. That means time path will oscillate, okay. So our time path will oscillate when these two conditions are applied. Our time path will oscillate between, minus 1 and we have minus 0.8, okay. Our b is greater than minus 1 and less than 0. So let me draw the graph to make it more clear. Okay, let's draw a small graph. So if we have t on this side and bt on this side, okay, first we have shown that our b is less than 1, that means time path will converge. Here b is minus 0.8, that means it will converge, okay. B is less than 0 also, because minus 0.8 is less than 0, so time path will oscillate, and it will oscillate between negative 1 and 0, okay. And let's show it on the graph. So what is our function? We have bt is equal to, we have minus 0.8 t, okay. When t is equal to 0, when t is equal to 0, what is bt? Bt is this very thing, that is minus 0.8 raised power 0, so it will come out to be 1, okay. When t is equal to 0, bt is equal to 1, okay. Let us say this is 1, okay. After that, when t is equal to 1, t is equal to 1 in this expression, so it becomes minus 0.8 raised power 1, so it comes out to be minus 0.8. Since we have discrete time interval, we will have the step function here, so our bt will be equal to minus 0.8. Let us say here it is minus 0.8, it is minus 0.8, 0.8, okay. So it is when t is equal to 1. When t is equal to 2, okay, when t is equal to 2, so we have minus 0.8 raised power 2. So square of negative number is positive, so 0.8 into 0.8 is 0.64, we will get positive 0.64, okay. That means our bt will be equal to 0.64, okay. And so on, it will go like this. It will shrink as t shrinks, and here we can see as t increases, t approaches to infinity, okay, bt approaches to 0, okay. As t approaches to infinity, bt will approach towards 0, okay. So all depends upon this base b, okay. This is how do we solve a difference equation and its economic applications. Thank you.